Welcome to another of our stats seminar. Today we're lucky to have Kayvan, who's been visiting us for about a month and a half now. Correct?
Yeah, 2 months.
2 months almost, yeah. He's an associate professor in statistical data science in the Department of Statistical Science at UCL, and a bi-fellow of Christ's College at Cambridge. Before joining UCL, Kayvan held postdoctoral as well as research positions at CMU and Cambridge. He received his PhD from University of Oxford. His research interests concern graphical Markov models, random network models, and special interest in conditional independence structures of such models. His works on related problems in causal inference and social networks. He works on related problems in causal inference and social networks and uses methods from algebraic statistics and combinatorics. The floor is yours.
Okay, thank you very much for having me. And hello to people on Zoom as well. So today, I've been working on this problem for the past 2 years. It took much longer than I thought, and we just very recently submitted it. It's on archive now. You can see the link here. Perhaps I use this. So you can see the link here. So it's a joint work with Terry Su, who is also at University College London. So it's about interventional distributions. So let's start with some basics. So there's no statistics really here. It's just very foundational work. So you will just see some sort of foundational theorems and ideas, so no data or real world data or any statistical analysis. So just to understand the difference between interventional observation and how it's used in causal inference, just a very simple example. Let's say this is hypothetical, but you would see correlation between smoking and the color of the teeth, right? But no matter how much you whiten somebody's teeth, their smoking habit wouldn't change. Whereas if you force something to smoke, it might be a bit unethical, then the color of their teeth changes, right? So that shows that smoking has a causal effect on the tooth color and not vice versa. So you see how causal relationships could be inferred from intervened distributions or interventional distribution and not from observations. Other than interventional distributions, there's a counterfactual approach to causality. We're not concerning this here. So the counterfactual approach is, so if this had happened, it would have, this would have happened, etc. And there are ways to sort of measure this. So in the literature, interventions in this type of intervention is basically usually under the class of statistical causal models. This is Pearl's work and people in CMU like Peter Spirtis and Clark Glimmer, etc. But this is not our assumption. So that's one of our main basically generalizations here. We are not assuming SCM, although I'm going to talk about SCMs because we use examples from SCM and those are something that we can really connect to. There is an axiomatic approach by Pearl. It's Pearl's do calculus. But the goal there is to see when these interventions can be identified using observational distributions. And that is not our focus here either. We are just defining what is intervention, what distributions are interventional, and in what sense they're interventional. So there are different types of intervention. The type of intervention we are concerned here, they're hard in the sense that they destroy all other causes. So if you intervene on something, it doesn't matter what causes were before, right? So they're gone. There are examples that this is not true. You might intervene on something and some causes might still, have some effect on the variable. And the other thing is our intervention is stochastic. So it replaces the marginal distribution of the variable with a new distribution. It's because some interventions are basically you put the variable, you force it to be a certain value. Here we are forcing it to be certain distribution. So it's more general in that sense. Okay. So let's start with structural causal models first to just get an idea. I assume most of you have seen this, some might not, but basically you have a collection of random variables. And the assumption is that there is a true causal graph. Again, we are lifting this assumption, as you will see later. But the assumption is causal inferences, there is a graph. We don't know it. We want to either learn it or estimate it, etc. And then in a more general setting, you can have arrows and arcs. Arrows are basically direct causes, and arcs indicate some sort of latent variables. I'll show it later. And then a structural causal model is basically a collection of equations where each variable is a function of the parents' variables, and parents come from this G. So this is a parent of this, right? So if J goes to I, we say that J is a parent of I, and by par I, we mean the set of all parents of I. So it's a function of the parents and some noise. So you have a system of equations here, right? So noises are jointly independent unless there is an arc. And if there is an arc, they are marginally dependent. So that's the idea. So I can show you an example. So here it's a very simple example, right? So let's say this is your true causal graph. Then this is the system of equation, right? So x4 is a node, x3 is a node, x2 is a function of its parent 4 and some noise. X1 is a function of its parent 3 and some noise. And because you have an arc here, we know that epsilon1 and epsilon2 are dependent, and other epsilons are independent. So epsilons are the noises here, right? So this is basically equivalent. It's not actually, this setting is slightly different than this setting, but let's not talk about that. This is kind of equivalent to saying there is a latent variable x5 that goes to x1 and x2. So when this is unobserved, that induces this arc between them. And these two settings are almost equivalent. Okay, so this is the SCM setting. So what's an intervention on SCM? Intervention is basically you replace the corresponding equation with a new distribution that is independent of everything. Like if I intervene on 1 in this previous example, I replace this equation with just this equation, right? And what does it do with the graph? It basically disconnects the causes. It keeps the children, so there's no children here, so maybe this was not the best example, but it keeps the children. It disconnects one from its parents. So this is gone. And as you see here, this will be gone. So this arc will be gone as well. So it disconnects all the arcs as well. So that's what it does. Okay, so that's the SCM setting, and SCM utilizes the theory of graphical models, because as you saw in this original example, this type of causal inference really depends on dependencies and independencies among these variables. This is how we talked about this sort of smoking. It was about dependency and independency. But a more general setting might have conditional dependencies and independencies, right? Okay. So what's the objective of the talk? So we want to provide some basics of graphical models and basically some new results that we need. But then more importantly, we provide some axiomatizations of family of probability distributions to be different types of interventional distributions. So you'll see those axiomatizations and what I mean by them. So what are the advantages of the setting I'm proposing? It has several advantages. One is that it does not make any use of modeling assumptions like SCMs or anything. The interventions are only on single variables, so you don't need joint interventions or concurrent interventions that you need in SCM setting. It is quite general, so it allows for these latent variables that I show, but also causal cycles. So you can have directed cycles in your graphs. And this was actually the sort of original motivation we had when we started this research. And that is that we do not assume that there is a true causal graph. So causal graph is really a byproduct of our theory, as you will see. So we do not start with a graph. We basically make a causal graph using our axiomatizations. Okay, is it clear, these? Okay. So we will define the causal graph and we discuss some theory related to the causal graph we define. And we also show that a large class of structural equation models or structural causal models are actually, could be embedded within this theory, basically. The natural ones, the good ones are really all there, okay? So let's start quickly with graphical models. So graphical models uses conditional independence, and conditional independence basically is like independence, but in the conditional world, conditional Z. So you can factorize if there is a density, you can factorize the density, for example. And usually in graphical models, we use this short notation. So we have this vector xv that I showed before, a, b, and c are subsets of v. So instead of saying xa is independent of x sub b given x sub c, we simply say a is independent of b given c. So that's just a short notation. So graphical models use graphs, and graphs are exactly the type of graph you saw in the SCM, right? So nodes are random variables, edges indicate some type of conditional dependencies. So in the SCM, we said edges are some type of causal, they have causal meaning here, they have only dependence meaning. There are ways to connect these two together. So in causal models, graphs with different types of edge have been used, and these basically mean different types of dependent structure. Here, like what I showed, we focus on arrows and arcs. And they have the same, they will have the same causal meaning as you saw. So these are direct causes, these are latent variables. So the types of graphs here, as I said, they allow for our arrows and arcs. We allow for causal cycles, and particularly even between two nodes. So you can have arrows in different directions. What we do not allow is multiple edges of different types. And there is a good reason for that. You can see that using only interventional distributions, there is no way to distinguish these in causal in SCM setting even. Okay, so we call these graphs bowless directed mixed graphs, but this thing is called a bow in the literature. So these are directed mixed graphs, but they don't have bows. Okay, just a definition, the same way we define parents, we can define ancestors. So ancestor will be a parent of a parent of a parent or something, okay? And we use this, because we use this a lot. So ancestor of J means the set of ancestors of J, okay? So we allow for directed cycles, so you can have a path from I to I. For ancestral graphs, I mean, this is defined by Thomas Richardson, who I don't know if he's today, I think he was busy today. So we don't assume this, but theory gets simplified for this. So ancestral graphs are basically graphs that do not have directed cycles. And also they do not have an arc with one endpoint being the ancestor of the other. Should I draw it, or is it clear? What there's an arc. You do not allow an arc such that one endpoint goes to the other with a direct path. So most theory of STMs is on directed acyclic graphs where there is no cycle and it's just directed edges. Some on ancestral graphs, and very recently there are some results on graphs with directed cycles. But SCMs do not work well with directed cycles, because if you think of these functional relationships, right? So if there is a cycle, you know, they get really entangled. So that you need real solvability assumptions for these to work. So it's not trivial at all. Okay. So in graphical models, there is a concept of, these are still, you're still not in the setting that I want to discuss. We'll get there. But in graphical models, separation is essential, the idea of separation. For undirected graphs, which we do not discuss here, separation is something very simple. So it says if you take out a node or a set of nodes, whether two sets get separated from each other. If that's the case, we call them separated given this third set, right? So it's a very simple concept. For example, here, if you take J out, I and L get separated from K. So we have, for example, this statement, right? For bidirected, when the edges are bidirected, there is kind of dual to that. So it kind of captures the marginal separation. So if there is, for example, no edge between I and K, I is marginally separated from K. So given nothing, right? For DAGs, it's called D-separation. I don't know if you're familiar with it, but it's a bit, I'm not gonna discuss it. There is no point on it's technical, but there is a way to read off these separation statements from the graph for DAGs. And for even this very general type of graphs, there is something called sigma separation. So you can read off separations from these graphs with cycles and everything, right? So it's a generalization of this D-separation. But there is a way, but I'm not going to discuss exactly how that works, okay? But why is this important? Because then, then separation in graphs and independencies in probability distributions get related to each other, and that's the main idea of graphical models, right? And a simple way to do that is based on the concept of global Markov property. So it's a one-way direction. So it basically says you have a random vector, you have V here, and you have a graph with node set V. If there is separation in the graph, then there is conditional independence in the probability distribution. If this holds, then we say that P satisfies the global Markov property for G, or simply P is Markovian to the graph. So it's a way to connect graph and probability distributions. And this is basically essential for causal inference using intervention in SCMs. That's basically the main thing that is being used in the theory of SCMs. So there is a theorem that says joint distribution of SCM. So if you find a joint distribution of the SCM from the system, that is Markovian to its associated graph. And this is essential. And basically what we're trying to do is we are building our theory such that a similar theorem holds. So we make a graph, we have some distributions that I define, I make the graph based on that. And we have axioms such that this holds. And when this holds, the theory of SCM could be followed, it could follow through the theory. Our theory basically gets connected to the theory of SCMs because we have this common result. So this was originally proven for DAGs in Perl and recently for ancestral graphs and even directed graphs. Okay. Okay, these 2 pages I could have avoided, but we are using this fact. I just talk about it briefly. If you want, you can relax for a bit because then we get to the main part. So if you don't want to focus now. But basically there is another concept called pairwise Markov property. And that says that if you have 2 nodes that are not adjacent in the graph, there is no edge between them, then you should have I independent of J given their ancestors, their joint ancestors in the graph. Okay, so it's only between pairs of nodes as opposed to sets. And it's only given the ancestors. Okay, and in the DAG, if there is no edge, there is always such a thing. In the more complicated graphs, we need the concept of maximality. So there could be certain pairs of nodes that are not adjacent, but you can't separate them. So for maximal graphs, that doesn't hold, but it doesn't really matter that much. So we can, at the moment, we can skip that. At some stage, I might need it and I might get back to it. But basically, the result I'm going to use, which we proved for this very general case. So this result didn't exist for this very general case, but existed for simpler types of graphs, is that under these 2 assumptions on P, so we say P satisfies intersection if this independence and this independence implies this independence. You don't need to know exactly what it is. Composition is more natural. In probability 101, you've probably seen that this doesn't hold. So if C is empty, if I is independent of J and I is independent of K, I is not necessarily independent of J and K jointly. You have examples even in the binary case, right? So, but if these two are satisfied, then pairwise Markov property implies global Markov property. So let's say you are in this general Bowles directed mixed graph case, and let's say P satisfies intersection and composition. Then if P satisfies the pairwise Markov property, then it satisfies the global Markov property. Then P is Markovian to G. So this pairwise Markov property here is kind of acting as a basis for this whole independence structure you have in the graph, right? So from this, you can read off all the complicated independencies between the sets. So we will use this fact later. But okay, now we are at the main part of the talk where I try to explain the setting we are proposing. Any questions so far? I'm not checking the chat if you, yeah, but I don't think.
I have a question actually. Sorry, do you mind?
You go ahead, we can.
Yeah, so I was wondering, so there's this work on Beaufry acyclic path diagrams or whatever, Bob's from, so some of it came out of ETH and with Robin Evans, and then I think Matthias Durton has taken that and kind of ran with it, and he's done a lot of, so would you say that their interpretation of these models is somehow a subclass of yours?
Of the directed ones?
Yeah, what do you mean of the directed ones?
Like they allow for directed cycles.
They do, I think.
Yeah. I think the type of separation they're using is the sigma separation.
I see. Okay.
So it's the same type, same separation.
So they might be. So would that make them an example of the type of graph that you are considering here?
Yeah, I think this is a more general type of graph. Yeah.
I see. Thank you.
Yeah. Okay. So we want to define interventional family. We started with complicated things, and then we saw there is not much that is needed. There's just one simple axiom later that we need for it to work in the basic level. So we define a family of distributions. The set V is like as before. So we have a family of distributions. We call them P do I, like do in the parallel world. So this is a family of V, or like to say if V of size n different distributions with the same state space. Okay, so the only point is these all have the same state space. And then we think of each of these P do I's as the interventional distribution after intervening on some variable xi. So that's sort of the interpretation. But the main point here is these only depend on one I. So these are all single interventions. So you're intervening on a single variable. Okay. So you have this family of distributions, and we call it an interventional family. And then we define a cause, the set of causes using this family. So we say cause of K is the set of I's such that when you look at P do I, like you choose P do I here, so you intervene on I is dependent on K. So the interpretation is quite natural if you think of this as an interventional distribution. So when you intervene on I is still dependent on K. Therefore, I is a cause of K. And actually, this is the exact wording as what Perl does. So this is not something new. Okay, but keep in mind, this cause depends on all these families, right? Because this I changes with each family. So you need the whole family to define cause K, right? And then if you have a set, you basically put them all together. But so by convention, we do not say A is the cause of A. You can change that, but we are removing A from the set of causes. So is that clear? Okay. Then our first axiom, which turned out to be very important and quite natural when you use these graphical methods, is transitivity of cause. So we call the family a transitive interventional if there's a set of causes transitive. So if I is a cause of J and J is a cause of K, then I is a cause of K. Okay. For SCMs, this doesn't necessarily hold. But for graphs, it's kind of natural, right? So cause here is kind of like a directed path if you think of SCM, and that's what will happen in our case as well, right? So if you have a directed path from I to J and J to K, you have a directed path from I to K. So we would like that the causal relationship actually stays there. Okay, so that is our axiom. And that's pretty much our main axiom. And this puts some restriction on the family, right? Because of course, these P do I's gets sort of related to each other using this fact, right? Because this cause depends on all the family. It uses all the family, each of these, right? So it puts some restrictions in the family that we're defining. Sorry?
There's a message on chat. I'm not sure.
Okay. It's okay. It's just for me. It's
sorry.
Fine.
Okay. Okay, and we can have causal cycles here in this setting. We can choose families that lead to causal cycles, right? If K is a cause of I and I is a cause of K, then you have a causal cycle, of course. So this imposes or induces some pre-ordering on V. So if K is a cause of I, we can say K is more than I. And if it is I is not a cause of K. If they're causes of each other, then they're in the same equivalence class. So that's your causal ordering, really. Okay. So that's how we define cause. Okay, now we want to make a graph. And in order to do that, we need the concept of D-cause. For ancestral graphs, we don't know the graph, but if the graph if the graph is an ancestral graph, then this is the definition, which is much easier than this. So let's discuss this first, and then I'll go to the main definition. So we look at the set of causes of K, and then we look at this. So if after do I, and if we know all other causes, if I still is dependent to K, then we say I is a direct cause of K. It's kind of natural, right? So you intervene on I, you fix all other causes except I, and if I is still dependent on K, then I is sort of a direct cause, right? But somehow in the general setting, this doesn't work. I show you an example. So in the general setting, we need some sort of intervened cause, which is really what you saw in the intervention in the SCM. So you need to cut off the parents of I before doing that. I'll show you an example. But you don't know this intervened cause a priori, and you don't know the D cause. So you need an iterative method that jumps between this and this. I mean, it's finite and it's usually just a couple of steps to get both this and this. So in reality, you need to condition on this I cause sub I. So this I is really the node I, right? So intervened cause sub I of K rather than just cause of K. But it's just some technicality. It's not hugely important. This is, I think, is the main idea. And as you see, cause is a universal concept, right? It's just this marginal dependence. So no matter how large this system is, the relationship between I and K would not change because it's only this marginal dependence. Whereas direct cause depends on other causes. So if you add variables to the system, something might no longer be a direct cause, which makes sense, right? So if you have a direct cause, you can always think of putting something in between, right? So that this causes that and that causes this, right? So it's quite natural, this idea, right? Okay, so this is the example I wanted to show you. So we still don't have a graph. So we are back to the SCM, or let's say this is the graph. This is the SCM graph, right? As I said, STM is embedded in our setting. I'll show it to you, but I'm just using an example from STM. So if this is your graph, let's say, so, and causes, let's say, are ancestors, like we expect it to be in the STM. So here cause of K is J, I, and L, right? But the I cause I, you're cutting this parent of I, right? So it's the intervened cause for I. So cause of K will be only J and L, J and I. So L won't be a cause because this edge is gone, right? So that's the intervened cause, really, the real intervened cause. And the direct cause of K is only J, but that's the only parent here. So if you know the separation here, which I guess most of you don't, actually in do J, so when you cut this guy, do J in STM means cut this guy, right? J would still be dependent on K. That's obvious. There is an edge here, right? So this dependency always holds when you. But if you in do I, if you cut this, then I is independent of K given J. So the direct cause of K is only J, right? Because here you have independency, right? So I will not appear in the direct cause of K. So that's why we don't have an arrow from I to K. Right? So this is basically this definition, right? So basically this shows that this is not enough always. That's what it says. Sorry, this is a bit, okay. Okay, so if you use only the other definition, you might misidentify some causes, direct causes. And I'll explain this more at the end of this talk. If I have time, I might not, okay? Is this clear? Anything in the chat? Nothing in the chat, huh? No, okay. Okay, now I want to make the graph. So I don't have a graph. I just started a family of distributions. I imposed this transitivity of cause axiom. I defined the concept of direct cause. But now you kind of know at least what the arrows are in the graph I want to make, right? So they're the D cause, right? So I call that the causal structure. So basically, if K is in D cause J, direct cause J, I put an arrow from K to J. Okay, but then what are the arcs? We need to add these arcs. And keep in mind, we don't have any observed distribution yet, right? I haven't talked about an observational distribution. We only have this family of interventional distributions, right? That's very important. So we are making all these only using interventional distributions, right? Okay, so I define first the I intervened causal graph. So I make I intervened causal structure. And again, you can guess what this is. It's like the STM one. So I remove the parents of I from this causal structure, right? I cut the parents of I, and I call that I intervened causal structure. Then I want to put these arcs in the graph. So I do that using this definition. So I look at do I, P do I check whether J and K are dependent given the causes of J and K in the intervened causes of I. So when you have do I, you use I cause I. That's the idea, right? Do I is always associated with this I cause I. So if J and K are dependent, given the causes of J and K in P do I, it means that there is some sort of dependency going on in that intervened graph, right? But we know already that there is no causal relationship between J and K because we are only looking at the non-adjacent vertices. We don't care about, if there is an arrow, we have the arrow and we don't have a bow, so we don't put an arc, right? So we look at this formula, and if this holds, we know that these are dependent, we put an arc between J and K. So this indicates existence of some latent variable, basically. I can show that. And that's why we put an arc between J and K. Okay, so I made this I intervened causal graph. So what is my causal graph now? What is the real causal graph there? So from these GIs, I can make my causal graph by saying that, okay, the causal structure is simply this. Where are the arcs? Where are the arcs? If there exists an arc in one of these, in every GI, then I put an arc in my G. And then I have my causal graph. Oh God. I can put, I have my charger. Where's the, oh yeah, cool. Thanks for letting me know. Okay, is it clear how I'm making my causal graph? No? So basically I make this causal structure, then I make the I intervene causal structure, then I put arcs in the I intervene causal structure to get I intervene causal graph. Then from I intervene causal graphs, I get my causal graph. Okay, that's the idea. And it has exactly the property that SCM graphs have, that in GIPDO, there is no arrow pointing to G and there's no arc to G. Exactly. No, go ahead.
If you don't know exactly the location of interventions, but you know some of them, there still be, like, do you have to know everything possible about the intervention?
In this theory, right, if you want the whole thing, yes. But in principle, you can look at the marginal version. So, I mean, I'm not discussing it here, but you can have the marginalized version of the system. So you can only focus on the places of interest marginalized over all other variables in principle. So you can look at the smaller family, which is the marginalized family, and do all this procedure.
There won't be any incompatibilities.
No, but there will be more arcs because there will be more latent variables. If you're marginalizing over something that goes to 2 nodes, you will get more arcs. But there is marginalization for this. Okay, now how we made our graph, the parents are the decals, right? That's how we made this, right? This is actually not that easy to prove, but we can prove that there is actually now an interchangeable terminology between ancestors in the causal graph and causes in the interventional family. So I is an ancestor of K in our causal graph, if and only if I is a cause of K in the family, right? So the graph works nicely with the interventional family. So one important corollary of this is that if the set of causes of a variable is non-empty, then you at least have one direct cause. One of these causes must act, at least one of these causes must act as the direct cause, right? Because you know there is a directed path from I to K. Choose the parent of K on that path, and that will be your direct cause, right? So that seems quite trivial, but very important for the whole thing to work, of course. And then we can generate cycles quite easily. We can easily make examples of these families to have causal cycles. And as I said, that's not the case for SCMs at all. So that's one advantage we have over SCMs. And I can show that what we generate, it is actually Bolus directed mixed graph. You might even see it. It's not that hard to see. Okay, now one of our main theorems, as I said, Markov property is very important for the theory of SCM to work. So first this one, I can show that always, if I is not a D cause of K, I is independent of K given I cause. If I is a cause of K, that is trivial from the definition because we generated D cause when there is a dependency here, right? But this holds for the cases where I is actually not a cause of K as well. So we always have this. And if you look at this, this looks like the pairwise Markov property for P do I that I was explaining. That's why I gave you that result. And therefore, under intersection and composition, we have the global Markov property of P do I and this I intervene. So this is one of our main results, right? So let me say it properly. So let's say you have your family, which is transitive interventional. And let's say P do I satisfy intersection and composition properties. Then P do I is Markovian to the I intervened causal graph GI. Okay. So that's one of the, and then we can use all the theory of STMs that uses this result. Any questions? Okay. But so far, again, I haven't talked about any observed distribution, right? Now, okay, let's have an example, a quick example, then I will talk about observed. Then we have observational distributions as well. So what I want to say here is that all these edges could easily occur. All these types of graphs could easily occur. Let's say we have only two variables, and there is some P where they're dependent. So this is not our, so just some distribution P. So we can generate something like this. We can think of X2 as a function of X1 under very mild assumptions, or X1 as another function of X2, where U and V, let's say uniform 0. Okay. Then I can generate different interventional families. So some standard interventions will be just put the copies of these for phi. So this is one distribution, this is the other distribution, or use this psi to do that. And then they give us two causal graphs, which are basically arrows. So this family gives us arrows from I1 to 2, this one gives from 2 to 1. Okay. But if you choose this one and this one, then you will get arrows from both directions, right? So you get a causal cycle. And if you introduce a third variable X3 that is independent of X1 and X2, and look at, basically in the, let's say in the density setting, just multiply the densities, right? And then look at this family. Then you see that P3 is appearing in both here and here. Therefore, 1 and 2 are certainly, X1 and X2 will be dependent in this family, in P1 and P2. But we established that there is no causal relationship between them, therefore there will be an arch. So with different examples, we can generate all these graphs. So the point here is that this is an axiom, right? So we are not saying that we are giving you the right graph. That's the modeling question. Think of, I don't know, Kolmogorov axioms. You can come up with probability distributions that, or probability functions that make no sense, right? And still satisfy Kolmogorov axioms. Finding the right family of distributions is a statistical modeling or mathematical modeling question, right? We are just saying what are the properties of something to be able to be called interventional family, right? So that's an important thing. For SCM, that's not the case because you've already assumed there is a true causal graph. You've already fixed your causal graph. So the goal is to estimate that. So this is a different goal. Okay, any questions? Okay, I don't have much time, so I might skip some stuff, but okay, let's discuss some additional axiom. Observation. So now let's say we want to include some observed distribution. So we say that this family is observable with respect to an underlying distribution P if we have this axiom. This one is the more important one. So basically, if for distinct J and K, we have J independent of K given causes in P do I, then J is independent of K given causes in P. So P has this property. Okay, if that's the case, then we say this interventional family is observable with respect to P. And if we have this, then we have our second theorem, which basically relates P to the actual causal graph. So again, if P2 is a transitive, now observable interventional family, it satisfies this axiom. And if P satisfies intersection and composition property, then P is Markovian to the causal graph G that we made, right? So this is the second Markov property type theorem we have, but this is for the observed distribution. And if we have the other direction of that axiom, we call it strongly observable. So if we have independence in P implies independence in P do I, then actually you can make this graph somehow using P. So that's the structural learning issue, right? So you can make this graph using P only. And you can show that if these graphs are maximal, which I explained doesn't matter, so somehow this G of P is the same as this G P do that was made using interventional distributions. So this will be related to structural learning problem under if you have this axiom in addition. Okay, is it clear? Okay. Okay, one other axiom now, to one other type of interventional family. So what have we done so far? We discussed, okay, first we only used interventional distributions. Then we introduced an observable distributions, observational distribution. And we say that, okay, we can detect these cause, whether there is a causal relationship or not using P. But the axiom was only about with independencies and dependencies between P and P twice. So there is no way to measure causal effects using that. So that's only about whether there is some causal effect. So this is a more restrictive axiom, which actually relates the actual distributions, not just the independent structure of the distributions, right? So, and this is why we call this a quantifiable intervention. So we say that this family is quantifiable interventional if, again, there exists an underlying distribution P such that this holds. So in do I, so if you intervene on I, and if you observe Xi, you have two cases, like given Xi. So this is probability of basically X, J, and K, given their causes and Xi. So if that is equal to probability of J and K, given only the causes, if I is not in the causal set of J and K, but you need to keep this Xi in the conditioning set if I is indeed in the causes of J and K. So you have two cases. If I is in the causes, you need to keep it in the conditioning set when you talk about P. And if I is not in the cause, then you can drop Xi from the conditioning set. Okay, so if this holds, then we say that this family is quantifiable intervention with respect to this P. And then I can show some results under this axiom. The first one is that the independencies are somehow preserved under quantifiable intervention. So if J is independent of K given causes in do I, J is independent of K given causes in P. And therefore, bivariate quantifiable interventional families are strongly observable. So this axiom implies the previous axiom that was about observable distributions. Therefore, we still have this Markov property I discussed, right? But another thing, if the graph is a DAG, then this P is actually unique. This P is uniquely identified. But that requires no latent variables, which makes sense because there could be many different types of latent variables that lead to the. So of course it can't be unique. But for a DAG, in fact, this P is unique under intersection composition. Does that make sense? Any questions in the chat? Is 5 minutes okay?
Yeah.
Okay, then, so these are the three main axioms we had. For structural causal models, if we have these two assumptions, which are pretty weak assumptions on SCMs, then basically they are in the setting of our paper. So what are the assumptions? One is what we call the converse pairwise Markov property. It means that if there is an edge in the graph, in the causal, in the graph associated to the SCM, if there is an edge, then we expect them to be dependent given their ancestors. And the other one is if you see an arrow in the graph, that is really a decause. That you haven't put an arrow for no reason. So that really should be a direct cause. If we have these two assumptions in the SCM, which happen for most natural SCMs people work on, it holds for them, then I can show that actually, if I generate this family using SCMs, that family will be strongly observable. So our axioms are satisfied for SCMs. And also, if I generate the graph we make, so if we generate our causal graph, it will actually be equal to the graph associated to SCM under these assumptions. Okay, so these are really the same graphs, the two interventional graphs or causal graphs. Okay, so these I lied a bit. So these are true for ancestral graphs. If you want it to be true in the general case, you need to assume that causes are transitive as well in the STM, which is not the case, and it's not that trivial when causes are transitive in the STM. We thought about it. It's not as surprisingly, there is no results on that. So STMs have been around for, I don't know, 40 years, and somehow there is no nice result that says when the cause is transitive in STMs. I guess you guys see the difficult question, right? Okay. Okay, I think I'll skip that, but basically what I'm saying is there are certain cases when the graph is non-ancestral and non-maximal, meaning there are missing edges that are not any, that there is no separation for them. For these cases, which is called primitive inducing paths, if you're familiar with the graphical model literature, this only doing single interventions might misidentify some direct causes. So there are different types of these primitive inducing paths. For some types, this our iterative procedure works. That's why we have this iterative procedure. For some other types, we can fix it by looking at another interventional family in sort of in the inside of the graph. So this type is fixable. So the only type that is not fixable is when you have several of these primitive inducing paths between a non-adjacent pair of nodes. So if you have and you know exactly how it works. So if you have R primitive inducing paths between a non-adjacent pair of nodes, then you need an intervention of size R. So you need to concurrently intervene on R variables to be able to detect that whether there is a direct cause or not. So we know exactly when single interventions work, and we know that in these complicated cases, how many concurrent interventions we need in order for us to be sure whether there's a direct cause or not. So there are certain cases our theory does not work with single interventions. Okay, summary, it's a 2-page summary. I'm sorry. Oops. So we have provided a general theory of causality. What are the advantages of it? It does not need to make use of any modeling assumption like SCMs. It only relies on interventions on single variables. It doesn't need joint interventions. It includes most cases with latent variables and causal cycles. And more importantly, it does not assume the existence of a true causal graph. This is really, so this might be a bit more philosophical nature, but it's quite important. You do not assume there is a causal graph. You just assume your axiomatizations and you generate your causal graph in a sense. So we did this by defining a new concept for direct cause and also intervened causal graphs. And then we provided some axioms. For when you have only interventional distributions, we show that transitivity of cause is key for the theory to work. When you have observational distributions, in order to detect causal effects, you need this observable interventional axiom. If you want to measure causal effects, you need something more specialized, which is this quantifiable interventional, which actually implies observable. So our main result basically is that interventional and observational distributions under these axioms are Markovian to the causal, the intervened causal and the causal graph we made. And therefore, the existing theory of causality that relies on this Markov property follows. And we showed that most natural structural causal models are embedded in this setting. And we identified cases where single interventions may misidentify some direct causes. Yeah, okay, thank you very much.
Questions, I guess, from the audience or Zoom? The new feature, right? Yeah, that it moves. It never used to be a. It used to be a static. Sorry.
Yeah, thanks, Kayvan. This is very interesting. Can I ask a question?
Yeah, go ahead.
Cool. Right. So this is very cool. It's a very cool theory. Yes, I'm wondering, I guess, how do you have any ideas of how you would use this for discovery, or is that?
I think one practical advantage, two practical advantages. One is with causal cycles, life is much easier with this theory than with the SCM. So I think really in practice for causal cycles, this could be very helpful. But secondly, the fact that it only relies on single interventions. So you know exactly in practice when you only need single interventions to work out what's happening. And when you possibly need multiple interventions for causal. I think these are the two main things I can think of in terms of practical advantages. And perhaps checking the quantifiable interventional for measuring causal effects could be helpful. I don't know, I haven't thought much about the actual applications yet. We just finished this. But it will have some philosophical implications, I believe, as well, with assuming that we don't need to assume there is an actual causal graph and what transitivity means for causality, etc. But there might be more of philosophical nature.
Can I also ask a follow-up on, well, actually, is it okay if I ask a follow-up? Okay, great. So yeah, this whole bow freeness of this graph, is that somehow, does that end up being a restriction or actually not a restriction? I couldn't.
Well, if you start only with interventional families, there is no way to distinguish just an arrow and a bow.
Yeah.
If you have some actual observational distribution, not just independencies, but the actual distribution there, then there are some methods to distinguish. But in the setting we have, for sure, there is no way to go beyond that. So in that sense, it's not a restriction, it's just a byproduct.